everybody. So today we're looking at a whole new concept, and that concept is a quantity that we call the mole. Now, the mole functions just like the dozen functions in our everyday life. We use a dozen to refer to 12 eggs, 12 roses, 12 donuts, really 12 of anything, right? So 1 dozen is equal to 12 objects of our choosing. The mole functions the same way in chemistry, except that it does represent a whole lot more of very tiny particles. So much larger number of much smaller particles. A mole is equal to 6.02 times 10 to the 23rd particles. Now that's 6.02 with 23 zeros, so it's a huge number of particles. The particles that it typically refers to in chemistry, that is atoms, molecules, formula units. It could be 6.02 times 10 to the 23rd ions, or people. That's a lot of people, 6.02 times 10 to the 23rd. It's a very large number, and chemistry particles are very, very small, and so it makes it ideal for actually counting in chemistry. Now, what we typically use it for, most commonly, is counting by mass. Now, we can use a balance to find the mass of substances, and if we know the molar mass, that's actually a way of counting in chemistry when we can't actually count individual particles because they're too small. Now, the molar mass is actually the mass in grams of 1 mole of any substance. So 1 mole, remember, 6.02 times 10 to the 23rd particles. So we measure that mass in grams of any substance, okay? The technical unit when we're using molar mass is actually grams per mole, which makes sense. The mass of 1 mole. So mass, 1 mole. Grams per 1 mole, okay? Now, the molar mass of any substance is numerically equal to the atomic mass from the periodic table, right? So remember that the atomic masses are the decimal numbers, 2 decimal places all along here, and they are measured in AMU, whereas molar mass is measured in grams per mole. So it's the same exact number, you just change the unit from AMU to grams per mole, right? This is how we abbreviate grams per mole. I know it's not a great abbreviation for mole, but G over MOL. So we can use the periodic table to find those atomic masses. We can calculate the molar mass then of Fe. How? We find Fe on the periodic table. We see that its molar mass is 55.8, or its atomic mass is 55.85 AMU. Therefore, its molar mass is also 55.85, but the unit is grams per mole. For sulfur, we find sulfur on the periodic table. Its atomic mass is 32.07 AMU, so its molar mass is 32.07 grams per mole, right? It's as easy as that, all right, to find the molar mass of an element. It gets only slightly trickier, not much, to find the molar mass of compounds or molecules, all right? So we can calculate the molar mass of several different substances. Let's start easy again. We know that 1 mole of anything, doesn't matter what we're working with, zinc, water, oxygen, or NaCl, is equal to 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd. The difference is, what kind of particle is it? And we've seen these particles, atom, molecule, formula unit, in our previous units. So, if I have 1 mole of zinc, well, what is the representative particle for zinc? It's an atom. That's the smallest representative particle. So 1 mole of zinc is equal to 6.02 times 10 to the 23rd atoms of zinc. Now, it is important that you are including a unit and a substance. Unit, substance. How many grams is that? Well, again, we find zinc on the periodic table. Its molar mass is 65.39 AMU. Or its atomic mass. So its molar mass is 65.39 grams equal to 1 mole. Do you see where that grams per mole is coming? Grams equal to 1 mole. All right, so that would be the mass of 1 mole of zinc. So grams of zinc. All right. For water, slightly different. We still have 6.02 times 10 to the 23rd. What's a representative particle for water? Well, is there a metal here? Nope, no metal in this compound. So this has to be a molecule. So this is molecules of water. 6.02 times 10 to the 23rd molecules of water is equal to 1 mole of water. How many grams is that equal to? Well, we look on the periodic table. We find the molar mass of hydrogen, 1.01, and the molar mass of oxygen, 16.00. Now we actually have to do a small calculation. We have 2 hydrogens in H2O. Each hydrogen has a mass of 1.01 grams per mole to give us 2.02 grams per mole. There's only 1 oxygen. It has a molar mass of 16 grams per mole from the periodic table. 1 times 16 is 16. And when you add 2.02 plus 16, you get 18.02. So 1 mole of water is equal to 6.02 times 10 to the 23rd molecules of water is equal to 18.02 grams of water. That's what we just calculated right here. Let's look at oxygen. 1 mole of oxygen is equal to 6.02 times 10 to the 23rd. Is there a metal here? No metal. So again, this is molecules of oxygen, right? Molecules of water, molecules of oxygen, right? Neither of them have a metal in them. How many grams of oxygen is that? Well, we have 2 O's, so 2 times the molar mass of oxygen, 16.00. 2 times 16 gives you 32 grams per mole. So you have 32.00 grams in 1 mole of oxygen, right? So grams of oxygen. All right, our last one is again going to be a calculation. 1 mole of NaCl is equal to, again, 6.02 times 10 to the 23rd. What's the representative particle? Well, Na is a metal, so this time it's not a molecule, it's a formula unit. So 6.02 times 10 to the 23rd formula units of NaCl, right? Now, again, we need to calculate that molar mass. So we have 1 Na. Molar mass is 22.99 grams per mole. And we have 1, oh, I didn't highlight it. Oh, yeah, I did. Chlorine, 35.45 grams per mole, okay? So 22.99, 35.45. We have 1 of each of them, so that's easy math. So what's 22.99 plus 35.45? 58.44 grams per mole. So 1 mole of sodium chloride is equal to 6.02 times 10 to the 23rd formula units of sodium chloride is equal to 58.44 grams of sodium chloride. And that's it. Calculating the molar mass. Now, we can use this all one step further to actually interpret the balance equations that we've been, balancing lately and giving the class of reaction for, right? So here's our example. Again, this says interpreting balanced equations. So if it's not already balanced, you would need to balance it. This one is balanced for us. So there's 4 ways that we're going to actually interpret this balanced equation. The first one is in terms of particle picture, okay? So what that means is that we're going to draw out what we see here in a very simple model. So I have magnesium here, so I'm going to draw a circle for magnesium and write Mg in the middle. I only have 1 of them, so I just have 1 circle. I have hydrogen chloride, except that it is an acid because it's aqueous, so this is hydrochloric acid. I have 2 of them, and it's an H attached to a Cl. H attached to a Cl. Notice that they are attached, right? So the bond here between H and Cl is represented by the fact that H and Cl are touching. But there's 2 of them, so I need to draw 2 of those. Right? HCl. I really should have made these circles the same size as that one. 2 HCl's. Great. On the other side of this arrow, I have 1 H2. Well, 2 H's are attached to each other here, because it's H2. So we have H and H attached to each other. There's only 1 of them, so here's 1 H2. And then I have Mg bonded to 2 Cl's. I'm going to do a little Mickey Mouse ear action here. 1 Mg attached to 2 Cl's. Mg, 2 Cl's, and only have 1 of them, so there it is, right? So that's interpreting based on a particle picture. It's just really showing what we have in terms of atoms bonded together or not. For representative particles, we're again going to bring back that atom, molecule, formula unit, representative particles. All right, so the great thing about these coefficients is, yes, it tells us how many little pictures to draw. It also tells us how many representative particles we have. So this is an imaginary 1. So I have 1. What's the representative particle for magnesium? 1 atom of magnesium. It's not bonded to anything, so it's just an atom. Plus, I see a 2. 2, okay, what's the representative particle of HCl? Is there a metal? No. So it can't be a formula unit. It has to be molecule. HCl. Notice that it's unit substance, unit substance. We're including both. Okay? Now over here, I have coefficient 1, so I only have 1. What's the representative particle for H2? There's no metal, so this is a molecule of H2 plus 1. Representative particle here, we have a metal, so it's formula unit of MgCl2. Okay, there's representative particles. Well, the great thing about coefficients, again, is that they not only tell us how many little pictures to draw, they also tell us the representative particles. They also tell us the number of moles. So that's easy. I'm going to change, the only thing here is I'm going to change the representative particle on each one to mole. So I have 1 mole of magnesium, atom to mole, plus 2 moles of HCl, molecule to mole, plus 1 mole of H2, molecule changes to mole, plus 1 mole of MgCl2, formula unit changes to mole. Ha, great. All right, so that's it for those 3. Pretty easy. Now the last thing is we actually want to know what the mass ratio is, not just the moles, not just the representative particles. We're going to use the molar mass to figure this out. So what we're going to do is we're going to take our basic structure here, 1 mole of magnesium, and then we're going to plug in the molar mass for each of these to actually cancel out those moles. So magnesium, right here, 24.31 grams per mole. Now watch what happens when we actually go to multiply that out. Mole of magnesium, and you're left with grams. And we're going to add those grams together to see what we get at the end. All right? So plus 2 moles HCl. The molar mass of HCl is 36.46 grams per mole. Yields, okay, again, mole cancels out. 1 mole of H2 times the molar mass of H2 from the periodic table, 2.02, because we have 2 times 1.01 grams per mole, plus, oh, and moles cancels out, 1 mole MgCl2, all right, and the molar mass, I had to write this down, 95.21 grams per mole is the molar mass of MgCl2. Moles cancels out, all right? The next step is just to multiply this out. So 1 times 24.31, 24.31. Moles is canceled out, so it's just grams of magnesium. And we do the same thing all the way across. 2 times 36.46 is 72.92 grams of HCl. Yields 1 times 2.02, 2.02 grams of H2. 1 times 95.21, 95.21 grams of MgCl2. The reason we're doing this is we want to see, does the mass of the reactants equal the mass of the products? Because the law of conservation of mass says that they should. So we add them together, and we get 97.23 grams of reactants. Add the products together, and we get 97.23 grams of products, right? The idea being, if those two aren't equal, then we haven't satisfied the law of conservation of mass, and something's wrong with everything we've done here. All right, so that's it, using the mole in counting by mass.